Oh, hi everyone. Hi. So welcome back. So today we actually start to talk about something really important. That is division. So far we have not really ever just discussed about our different division in arithmetic. Remember, we have very slowly and painfully talk about addition, then multiplication, and subtraction. The reason why we wait so long to discuss division is because division is really something very kind of conceptually important and difficult. It's the transition from what we mean by integer, which you may recall on our number line. We have 0, 1, 2, 3, and so on. Then after we introduce negative integers, when we studied subtraction, we also get -1, -2, and so forth. So that's what we have been learning about numbers. But clearly, there are many points on this number line that we have not actually studied at all, because all we know are those isolated points, right? Division, however, will help us to gradually expand our numbers on the number line from all those integers into something we call rational numbers. And this truly is a significant step. So we will see how this happens. But more importantly, once we have a division, we will be able to study some fundamental or very basic number theories. Okay, so far we have not been able to do that because we don't have our super important arithmetic operation, division. But before we talk about division, let's quickly recall how we have developed our number systems and the associated arithmetic operations so far. Okay, so recall that we first get addition, and we realize that addition is nothing but repeated counting. To that, we first need to have a starting point number, which is 0. Then we have 1. From that point, once we have this so-called increment operation, we will be able to, one at a time, add all the numbers into the our system. So 0, 1, so let me see if I have, yes. Okay, so 0, 1, 2, 3, 4. So addition is nothing but what we call repeated counting. Okay, well, there is a very important property associated with those numbers that we have never discussed. That is that if we have those natural numbers from 0, 1, 2, 3, 4, and this addition operation, so that we can operate on two natural numbers to get the other one. An important question is that when we do that, will the new number that we get is still a natural number? For example, if we have a number 3 and we have a number 5, we add them. We know we can get the result by counting, and then we get a result which is 8. 8 turns out to be also a natural number, right? The question is that, is this always true? Will we always get a number that is natural number if we perform this addition operation on two natural numbers? It doesn't take too much time to verify that this is always true. So you can see that, remember at this point, we do not have negative numbers. We only have non-negative integers, so that it's on the number line, they only go this way. So any two such numbers, no matter what they are, say 127 plus 2,567, no matter what they are, we will also get another number that is somehow in our natural numbers. If one of them is 0, it doesn't do anything to the addition, so immediately we get one of the two numbers itself. But that once again shows that the result is within natural numbers. This is actually a very important property, what we call closeness. So with respect to the numbers we have discussed, 1, 2, 3, 4, 0, those numbers, and the associated addition. We call this those numbers are close with respect to the addition operation. Well, this is a very important concept, but we don't have to discuss it too deeply, because this will be actually studied in higher math in college, which is way too just advanced for you guys. But we want to mention here to show why we want to introduce first negative integers, then some additional numbers beyond integers. So from that addition, we got multiplication. Well, multiplication is simply repeated addition. So if we get 3 times 4, we know we add 4 3 times, or with associative property, we can say we add 4 3s together. So either 4 copies of 3 or 3 copies of 4, but either way, we get 12 by repeated addition. Now, the question is multiplication an operation that allows this closeness? So let's think about it. We have 0, 1, 2, 3, 4, all the natural numbers. And we have this multiplication operation. Can we claim that those natural numbers are close with respect to this multiplication operation? Well, it seems that they are. Given any two natural numbers, with or without one of them being 0, when we multiply them, we always get another natural number, right? You cannot find a single counterexample, because if one of them is 0, we get 0 as the result. If neither is 0, then any two positive integers, when we multiply them together, the result must be another positive integer. So that meets our definition for this closed list with respect to multiplication. So indeed, both addition and multiplication keep this closed list property for natural numbers. And that's exactly why we did not have too much trouble develop those operations and associated with the numbers. Remember at the very beginning when we discussed the history of numbers, we briefly mentioned that people struggled with subtraction, right? Before we even understand subtraction, you will have to ask yourself, if we have this operation 3 subtract 8, what will we get? Now we know, as we have already studied, this will give something that is not actually natural numbers. What will we get? We get a negative number, which is -5. In this case, a negative integer. So clearly, natural numbers are not closed with respect to subtraction. So if we have 0, 1, 2, 3, 4, and the subtraction operation, clearly we are not close, because if we have two arbitrary integers and perform a subtraction operation upon them, we may, but we may also not get another natural number. If we have 8 minus 3, yes, we will get 5. But if we reverse that, when we do 3 minus 8, we will only get a number that we did not previously have. And for that reason, we actually expand our number system from natural numbers into integers. Along the way, we define all the negative integers. So after expanding our numbers from natural numbers to integers, we have all those negative integers, -1, -2, -3, and so on. Now can we claim that after this expansion, our numbers are closed on the subtraction? Remember, the definition of closedness in this case is that if you have any two such numbers, now remember they can be negative integers as well, when we do a subtraction operation, where we always get another number that is still within this expanded number system. That means that now we don't have to leave the result with a natural numbers. As long as the result is an integer, we're okay. And the answer is yes. So any two integers, whether they are something like 8 minus 3 or 3 minus 8, we will always get another integer. Okay, so indeed, integers, no, this is not natural numbers. Integers are closed with respect to subtraction. Okay, so far so good. That's what we have. Now, think about something that we are actually familiar but also unfamiliar with. That is subtraction, division. Now, think about division. We have known division for years, right? But probably we have never discussed division from the perspective of what we have just discussed. So what is 6 divided by 2? Well, what is this? We have not even defined it. Remember, so far, every step of the way, we have to define what an arithmetic operation is. In this case, how do we define it? We already know this should give us 3, right? We have already known this. The question now is, how do we define division so that the result is consistent with what we actually knew and makes sense? But before doing that, we have to answer this question. Once if we have defined division according to our understanding, then are all the integers close with respect to division? Look, we have 0, 1, 2, 3 from in this direction. Then we have -1, -3, -3, -4, and so on. If we define division according to the way that we have understood this operation, will those integers be close with respect to division? The answer is no. First of all, when we define division, as you well understood, we cannot allow the divisor, which is the second operand number in this operation, we cannot allow this to be 0, right? So 0 is not allowed. But that does not suggest that after we add this limitation, that doesn't mean that we cannot have closeness. But the problem becomes apparent if we say we want to divide 3 by 2. What do we have 3 divided by 2? Well, at this point, you already know we will not be able to get an integer result in this case, right? What we will get is a quotient, in this case, a quotient, and then a remainder, which is 1. So this is not actually strictly what we should get with respect to this division operation. The reason is that for this operation, strictly speaking, we actually get 2 results. They work together. One is the quotient, and the other is the remainder. So we need to take care of how we can handle this particular situation. Okay? Okay, so that's the significant just a roadblock we have. How can we handle something like 3 divided by 2? The result will not possibly be another integers that we have. Yes, we have a quotient 1, but we also have a remainder 1. Those are 2 numbers, not just one single number. So that doesn't sound good for our operation that we have so far, because when we say we have operation, we want to get a single and determined result. So what we actually have here is a division with remainder operation. For this particular operation, what we get is a quotient and a remainder. But what if we don't have a remainder? Let's say we have 4 divided by 2. Don't we have just one single result? Well, yes and no. Yes, it's because we will be able to get 2 as the quotient in this case. We don't have any remainder. But if you think a little bit more broadly and open up your mind, you will see that we still have a remainder. It's just that it's 0, right? This is the remainder. So in that sense, when we have a division for 2 integers, we can always unify the 2 cases by saying that we have a quotient and we have a remainder. But it's just that in some cases, the remainder will be 0, while in some other cases, the remainder will be greater than 0. But at all times, it's important to also recognize that the remainder will be smaller than the divisor. Okay? This remainder, if it's equal to or greater than the divisor, then our division did not actually complete. We will be able to get one more, at least one more into the quotient. For example, if we have 7 divided by 2, will we get a quotient like a 2 and a remainder 3? No, it doesn't work because now the remainder is larger than the divisor, so we will be able to continue to get the quotient bigger. So we will actually make the quotient as 3, then we get a remainder 1. At that step, we will finish our division. So the conclusion is that division is something that we have not been able to easily define because of this situation. When we have 2 integers, when we divide one to the other, we may not get something that we know how to describe it. This is actually analogous and conceptually almost exactly the same situation when we have a division, right? Recall the problem we have a division earlier is that if we only have natural numbers, we may not be able to define what is 3 minus 8 because it will not give us something that we already have. We remember at that point, before we introduced the negative integers, we only had natural numbers. Therefore, we cannot answer this question. If we subtract 8 from 3, what will we get? To answer that question, we expand our number system from natural numbers into integers by including all the negative numbers. Now, at this point, we have a different but conceptually almost the same problem. We want to divide an integer. Remember, in this case, we actually have to deal with negative integer potential as well. So we have a situation like this. If we have 2 integers, we want to make sure that we will get something that we actually know what it is. Not in this case that you will get actually 2 numbers. We want to answer what will we get as a single number. That's the goal of why we want to study division, and we will see at that point, once we have properly defined division, we will be able to expand our number system once again beyond what we already have. That's the natural numbers. That's integers. So far, remember, we only have integers. But once we have properly defined division, we will be able to expand our number system into some points on this number line which we have never talked about before. And that is the rational numbers. Okay? And if we limit ourselves to positive rational numbers, we will get something we will call fraction. Okay? So negative fraction, by extension, we will also get that. But something like 2 over 3 or 3 over 2, both those numbers are fractions and are also rational numbers. And you may become curious, what is this thing separating the two? Well, as it turns out, in this is actually just the same division operation. But in this more general concept, when we introduce a fraction, this will be what we have. Okay? So it's really important to see why we want to withhold our study of discussion of division until now, because it's the most difficult arithmetic operations we will discuss. And once we have properly defined that, we will be able to expand our numbers from integers into rational numbers or fractions. Fractions and rational numbers are not, well, it depends on how you define it. They're not exactly the same, but in a way, they can be exactly the same. Okay? So that's what we will study next. I'm so sorry that my voice is still weak, so we will have a shorter session today. Next Wednesday, we will pick up from exactly we had right now, and to introduce what division really means. And from that point on, we will be able to discuss something really interesting, and we will adventure into just some basic number theory. We will study something called a division, Euclidean division lemma, which sounds interesting, a name for you. And we will talk about Euclidean algorithm. That will be something that we will study in the next several lectures. So those things will give you some idea why number theory is so important in mathematics. And Carl Gauss, the famous mathematician from Germany, once called that number theory is the crown of mathematics. Okay, so today is just a very very quick introduction of why we want to study division now and how significant this is. The concept of a division will allow us to understand fractions much better. Okay, so I will talk to you next Wednesday. All right. Sorry for the shorter session. I still have problem to talk for extended amount of time. One thing is for sure, this winter across America, we had serious flu problems beyond COVID. So be careful if you have not taken the flu shot. Actually, I just had it yesterday. No, I'm sorry. I had flu shot 2 days ago, and yesterday I just have the COVID booster for Omicron. That's why I'm still feeling weak and then my voice is a little bit shaky. Anyway, I will see you again next week. Bye now.